Hi, I'm Ed. I'm here to talk about OSS databases for observability. I and Brian, who's going to come up and do the second half of this talk, both work at Grafana Labs and build. I build Loki, he builds Pyroscope. And the goal today is to try to get folks to kind of appreciate why we have 4 of them and why you should want to use all 4 of them. Is anybody here using all 4 of these databases? Yeah, let's go. So if you are, there's some new features we're going to talk about, and be exciting to know what you are looking forward to if you're using them. If not, I'm going to start by kind of talking a little bit of a story about why we have these 4 databases. Starting with the best, in my completely biased opinion, signal, which is logs. This is how everybody kind of gets their introduction to observability. They build an application, the first thing you do to see if you can even compile an application is do a hello world example. And then it doesn't take long before you realize there's nothing I can do with logs, right? I can do everything. And quite a few years ago, this was the only tool that we really had for kind of understanding how our applications were working. And the result of that is that the world is very, very chaotic of logs. There's structure, unstructured, trying to get people to agree on formatting, space limited JSON. It's extremely difficult. And then we have applications and libraries that we didn't build, we don't maintain. So this is why we built Loki, was to have a database to aggregate logs that we could build to huge amounts of scales, and had no opinions on how that data got in there. So entirely schemaless ingestion. But kind of back to this sort of story on how we've evolved observability. I worked at a company many years ago that had a policy that basically said, always have a log line at the beginning and the end, not of every function, but most functions that would have a consistent naming scheme and then log the variables that went into and out of that function. And this was really handy, right? This allowed us to troubleshoot a whole bunch of production problems. But really, this is just tracing, right? So this was in the late 2000s. I think before tracing might have had its real origin story. But tracing is a superset of logging that gives you some really, really nice features, right? Like context is the big one. A trace ID that can be propagated through headers across HTTP boundaries and network boundaries to let you build visualizations, really tiny, hard to read visualizations in my screenshot, sorry. But let you see like what your app was doing and where and why and how long, and you can attach metadata to that and do a really good job of being able to see what your app is doing. And because this is a superset and a lot of this data is structured, this is why we built Tempo. Having a place and a way to store structured data and more efficient in huge scales. Loki is a row-oriented database. It's very, very simple data model to store strings. Tempo is a columnar-oriented databases and uses that metadata in columns to be able to more efficiently access that additional structure. But both of these databases have a problem of sorts, certainly a challenge, which is the amount of data that you can produce from logs and traces, right? You can. In this example, I looked at one of our Loki clusters for 15 minutes to see how many push request parsed log lines we have. We log some data around the push request we receive, and it's about 30 gigs in 15 minutes, 30-some thousand lines a second. And Loki's happy to sort of run these queries over hours, days, maybe a week, if you're patient, maybe a little bit longer. But there's just some limits to what we can do. We've made it very, very fast, but there's a better way. Metrics are the better way. So what metrics gain you is a way to sort of normalize that volume away from the application's behavior itself, right? So by turning these into counters, instead of having to log 1,000 or 10,000 events and count them, we increase a counter 1,000 or 10,000 times, and we sample it at regular intervals. And so now we get a fixed rate of data, and that lets us run short queries to be able to see, error spikes, or 7-day, 30-day, 6-month queries to be able to see, real trends over time. You can do this stuff in logs and traces. Sometimes, depends on the volume, right? Like, searching hundreds of terabytes of data can take a bit of time. So now we have this world, we have these separate databases. We built them to be good at what they're good at, right? The type of data they receive, how they receive it, how they store it, how they query it. And now we work a lot on how you work the best between them. So metrics and logs, for example, that error spike is a real thing. This is a production Loki cluster from a few weeks ago. In Explore now, I've turned that into a graph that I can see. And then using Loki, I pulled up the logs and did some normalization to extract the log messages to count the log messages by type. In this case, deadline exceeded comes to the top. If you're programming Go, deadline exceeded is a confusing way to describe a timeout. And so why did it time out, right? So I jumped ahead of myself here, but what I know about Loki, building Loki, this is on our right path. I got a timeout. We have a pretty tight timeout. You have to push request has to process in about 1 second. And usually when we can't, it's because we're CPU starved, right? Or something is saturating, or we're not provisioned enough for CPU. So now my sort of new favorite, or maybe second favorite to logs signal is profiles, right? So I can use Explorer again in the same time frame and same data to go look at what the CPU was doing. In this case, interesting story was some label-based access control work that we do uses regular expressions. Golang is not the best at regular expression work, and we were recompiling the regex sort of multiple times per request, and we found a way to remove that and essentially only compile it once per request to make those kind of error spikes go away. So this is how we sort of build and evolve our tools over time. And this is also why all of these things work really, really well together, and why you should use all of them, and why we work on building interactions between them. So logs can do recording rules to generate metrics. If you don't have the way to instrument your app directly, if you have traces and not logs, which is probably less common, but there are ways to generate metrics from traces as well. All of these things can leverage profiling to understand what your apps are doing. So whole big picture together. And what you end up with is this toolkit. And so now what I want to talk about for the next, say, 10 minutes or so, a little bit about metrics, a little bit about logs, and then Brian is going to talk about traces and a little bit about profiles. So apologies to all of my Mimir developer friends, because I have a lot less Mimir slides than Loki slides. Maybe because we just did a major announcement, but maybe because I work on Loki. I won't tell. But what Mimir is a open source, highly scalable, horizontally available, remote write backend for Prometheus style metrics. It also does support Graphite style metrics. What's new and really exciting that I do want to talk about is histograms. So if you're familiar with histograms in Prometheus, basically you go into your application, you define a histogram metric, you give it a number of buckets. You sort of need to know ahead of time those number of buckets. And then when you observe a value, it gets put in one of those buckets become series, and they produce graphs in the top here, like the one that doesn't have any units on the x-axis. But anyway, the problem here is you don't always know ahead of time what the right bucket is, right, or what the right bucketing strategy is, and that's a code change to go change that. So native histograms, also known as sparse histograms, or in OpenTelemetry world, exponential histograms. I actually kind of like the phrase sparse histogram, because that's really what they are. Is they don't require upfront bucketing. You can essentially add values to them. They take the values and determine the buckets and the number of buckets you need based on the value distribution. And what you get is better resolution in your histograms, both for heat maps and distributions, without having to do any of that work and having to know any of those buckets. So very, very cool. And then I mentioned when we went from metrics to profiles and metrics to traces, or sorry, metrics to logs, there's also metrics to traces in the form of exemplars. So given that metrics are probably the first tool that I go to most of the time, because it's kind of the fastest tool that I have for narrowing down timeframes and basically systems that are affected. And what you can do is you look at your graph and you get these little dots that show up all over them, and those are examples, exemplars. So those are exactly events that happen. You can pick one at the high end of maybe say a latency spike or something like that, and pull up a trace and say this was that execution event for that high latency event, and very quickly be able to find hopefully root causes to some anomalous latency events. So thank you, Mimir. Went fairly quick there, but I want to spend a little more time talking about Loki. So Loki 3.0 announced a couple weeks ago. Let's go. 5 years in, Loki turns 3. That's the phrase that my peer Owen coined, that it sounds pretty cool. I didn't catch this earlier. Our formatting is really cool on these version releases. But the story of this slide is, what we've been building over time. Richie mentioned in the keynote, we're really excited. Loki started as an idea. 5 years later, I would say it's proven to be a popular idea. More than 100,000 active open source installations. As part of our SaaS service for Grafana Cloud, we run numerous clusters that ingest hundreds of terabytes of logs, serve petabytes of queries. We've been able to build, y'all have a lot of logs, so we've been working to build, the biggest, most scalable system, and we've kind of, iterated on it a few times over the way, and the things I'm going to talk about now are these Bloom filters in particular, and some of the other new features in 3.0. I throw this slide in here too because the sort of evolution of the idea has come a long way too. Loki was built on this idea that you don't need a big index to be able to solve a lot of logging problems, and instead you can rely on distributed systems ideas, parallelism, commodity computing, and the capabilities of object stores like GCS and S3 to obtain query throughputs now that are in the hundreds to up to terabyte a second for searching your logs. And the economics of this are really fascinating because it's expensive to build an index and maintain a database with large indices, and it's interestingly cheaper to brute force your way through a lot of these solutions, kind of up to a point like we've found now where that kind of trade-off is, certainly for some types of queries, and that's what I'm going to talk about with Bloom filters. However, first I'm going to talk a little bit about OpenTelemetry because this was also new in 3.0. We're pretty excited about this, which is, we had kind of a missing piece here. So OpenTelemetry has some nice concepts around consistency in structured metadata. They call like semantic conventions. And Loki had two places to put stuff, an index and then a log line. Excuse me. And our index, we want to keep really, really small. We just want like a few key value pairs to define where the logs come from. The small index makes Loki a lot easier to work with. And this is maybe a bit counterintuitive sometimes, but the brute force strategy does actually work quite well. But what do we do with the structured metadata that came along with OTel, these resources and attributes? Because I jumped ahead of myself. We call it structured metadata. So what we did is we made a place in Loki that we can store structured data, which is not indexed and also not in the log line. And so that's where we put this OpenTelemetry resources and attributes. It used to be, I got to put these slides out of order, but what we did, the exporter would serialize the metadata in with the log line into the string field in Loki, and this is kind of a mess, right? So in order to get that data back out, you had to run a JSON parser initially just to get the metadata back where it belongs, and then maybe another JSON parser for your log line if it was JSON format. So now that is sort of all handled for you. We can store that data in its own place, and you get your log line as you would expect. So much better interaction with OpenTelemetry, and including the Loki has native endpoints now for OTLP, the OpenTelemetry line protocol. I don't know if that's what the L and the P stand for, but it's close. The last thing I want to talk about, though, that I'm kind of the most excited about is Bloom filters and like kind of how they work and how we added them to Loki and what we're trying to accomplish with them. The story here looks a little bit like this, right? We built this no schema ingestion log platform, and we did that because the world of logs is a chaotic nightmare. And that we like, that works really well. And so how do we, sort of improve on this in some use cases? Because like I said, we've been very good at building highly parallelized query workloads, but you can find limits of everything, and our cloud providers tell us that we're finding the limits, at least of what they want us to do without giving them more money. So that changes the economics of how we approach Loki, right? Like when you try to pull more than a terabit a second out of object storage in a consistent way, they start telling you that you're going to have to pay for more resources to do that. So this is where we also realize at the same time, a lot of the time our queryers spend querying, they're really not finding anything. In fact, 75% of the time that our subqueries would execute on a parallelized query, they matched no log lines. The filters in the query essentially excluded all of the log lines. So we have this huge amount of time that we spend not finding any information. So it's like the answer wasn't necessarily let's make Loki faster and parallelize more. It started to become like how do we search less, right? And what we found is that this use case that we see that kind of drives this behavior looks a little bit like this in most cases. It's someone looking for like a high entropy string, a string with a lot of variability in it. And then oftentimes over long time ranges, like a lot of times like a customer support case, they don't get much information other than an order ID or a trace ID, and they're expected to go search to find logs to help troubleshoot. And this is where people would search over, like namespace equals all of them for 7 days or 30 days, right? And poor Loki's just over there looking and looking and looking and not finding anything. So the problem was, how can we make that better but not have to impose more structure on ingestion, right? Like not have to impose anything at query time. We really want to keep schemaless. We really don't want to have the user experience change around queries. I say schemaless. I'm happy to always talk about schema stuff because it's a really interesting conversation. We tend to call it schema at query, where our query language imposes structure and things like that. So we wanted to kind of keep the same setup we have, and this idea that we were kind of calling negative indexing was born. What we realized is 75% of our time we're looking for data that we can't find, so how do we find less data? Wish I remember when that started to know how much time I have left. Sorry, Brian. Oh, 45, okay, I'm good. So the idea of negative indexing was kind of born here. And in particular, we're going to leverage a technique that I think basically every database leverages, which is Bloom filters. Bloom filters are a really clever probabilistic data structure. And they have this unique behavior of them, which is you feed a bunch of data into them, and then you can take a string. So you feed a bunch of strings in, you can take a string and say, hey, have you seen this string before? And it will tell you with 100% certainty, no, it has not. Or it will say, yes, I have, but I might be lying a little bit. And this works out really well for this case where we're trying to figure out where not to search, because 75% of the time we're not finding anything. So we can ask these Bloom filters, hey, have you seen this? And they'll say no, and then we don't have to search that data, and we don't have to worry about it. Or they say yes, and we go search it, and maybe it was there, maybe it wasn't, but they've removed a huge amount that we don't have to. So that false positive doesn't really hurt us that much. So I can't explain well how Bloom filters actually work. It's a series of hashing functions. Everything in distributed systems is hashing functions, just more and more hashing functions, and then you end up with some bitmap, effectively a bunch of bits that can be used to repeatedly answer that question the way that it does. And so what we decided to do with Loki here, our idea is to try, it's like, how do you get the data into Bloom filters? So we're using an approach called n-grams, which is a way to tokenize the log line into smaller strings. So this is how we want to approach this problem without having to know your structure, is we just don't care. We'll tokenize the entire line into n-grams, shove it into Bloom filters. We will then tokenize your query expressions and use those, the filter expressions, against then n-grams those, and then look those up in the Bloom filters and give us reasonably good confidence. Depends a little bit on kind of your entropy levels, right? Like, so long UIDs work the best. Long characters, short words, short strings. I'm always amazed the number of times if you took like a 5-digit number and just searched it in your logs, how much it just matches everything. Like 6-digit, 7-digit numbers and timestamps. Like, it always surprises me how random numbers will match. So you run into that a little bit more when you lack some entropy in your strings. But very excited about Bloom filters. Kind of early days. This wasn't 3 days ago, but it was not that long ago. But we have it working. We're working on sort of making it faster. This is a kind of a progression. Somebody at our company, maybe it's sort of wider, make it work, make it fast. I think it used to be make it right. There's one of those in there too, but we'll assume that we got that check in there. And so that is mostly what I want to talk about. I did have some slides in here around our new experience on querying. And I'm just kind of skipping them because you got to watch that video that was made around that earlier. So, but the goal looks like this, right? We want to have an entire queryless experience around how you enter and find your logs. So with that, I'm going to hand it over to Brian, who's going to talk to you about Tempo and Pyroscope.
So I'm Brian, and I want to start today by talking about Grafana's distributed tracing database, Tempo. And Tempo is really good at helping identify where latency and errors originate across services. So the Tempo team has been working hard on a few new great features: metric summaries, structural operators, and TraceQL metrics. So before we dive into the features, I just want to give an overview of TraceQL, which is Tempo's query language. And so here's an example trace quail query. And so this one run will select all of the traces that match each of these conditions. So in this case, we're looking for a service name appfoo, and we want to constrain to URLs that match the /API regex, and we want only status codes in the 500 family. And so with that, I want to review, kind of paint a scenario here. I'm an engineer. I'm working on some stuff, and I've just been paged that one of my services is reporting an elevated error rate. So to begin investigating, I want to find traces that have errors in them. And so I can do that with a trace quail query like the one shown here. So I run this, and I get a nice result set of all the traces that have an error in them. And so I can begin by selecting a trace, and I'm kind of browsing through here, looking at different spans and trying to find the smoking gun that's pointing to where this error is occurring and what service is causing it. And I don't immediately find it, so I open another trace and then another trace, and soon I have 20 tabs open, and my computer is crashing and my brain is out of memory. And I'm trying to find what's similar about all of these traces that can lead me to indicate where this error, what service is causing this error under what conditions. So there's a better way to do this. I can leverage metric summaries, and metric summaries allow me to aggregate by attributes that I suspect are relevant to the issue at hand. So this service I know is an API that serves HTTP requests, so I might want to aggregate by the endpoints that this service provides. So in this case, I'll aggregate by HTTP target. So I run that query, and I get a nice table breakdown aggregated by endpoint. And so I can see that I get some metric information for each endpoint based off the tracing data. And I can sort this error column, which tells me what percentage of these had an error reported them. And I can notice immediately that this account endpoint is suspect. This has a much higher error rate than the rest of these endpoints. And so this might be worth something for me to continue investigating. So Tempo has another trick up its sleeve. It can easily handle high cardinality attributes like user IDs. So here is an example of Tempo's TraceQL query builder. And first I'm selecting my service. And below you can see the TraceQL that's going to correspond to the settings of this query builder. And so I want to not only aggregate by my HTTP target, but also by user IDs. And so here now Tempo provides me with this result set, similar to the ones we've seen before, where we have a breakdown of account IDs, of accounts or endpoints, but also user IDs. And so I can again sort this aggregation by the error column, and I observe that not only is the account endpoint causing us problems, but there's a specific user ID that's generating the majority of the errors. And so this can be super useful because this gives me a nice breakdown of wide swath of tracing information and presents it to me in this way that I can easily respond to it. So moving on, I want to talk about structural operators. So as data moves through our systems and traces are built as a result of which, these traces end up having these very tree-like structures. So the Tempo team has been smart and has worked on a way to create query operators that leverage this structure. So these are called structural operators, and here's two examples of them. The first example is called the direct descendant, which in English, this is basically asking us what traces use service A and then immediately go and use service B. And the second one is asking what traces use service A and at some point have an upstream descendant that is reporting an error. And then finally, select the service names where those errors occur. And so circling back to this investigation I'm running, I can run this query asking for the service and this misbehaving endpoint and ask for all the upstream spans that have an error in them. And I get this nice breakdown, which gives me a list of all these spans where an error has occurred, and I can use this to then further analyze where this error is occurring. In this case, we can see, we have a lot of commonality in this db.name column, so maybe that's worth investigating why the database is reporting these errors. So these query features are really useful and can help engineers understand and pinpoint where latency or errors occur. But oftentimes there is a drawback, which means it requires you to write a query. And sometimes teams might not have new engineers on them who aren't familiar with TraceQL, and that means they need to learn the query language before they can effectively triage incidents that are occurring. Or there might be a team triaging incident who is familiar with TraceQL, but they're looking at a service that they're not familiar with, so they don't understand the attributes associated with that system and the behaviors associated with that system. Or we might just be a little bit lazy and want immediate results. Just tell me the answer. So in this case, the Tempo team has us covered here too. They're developing this new tool called Explore Traces, which presents this queryless trace analysis experience, where without having to write queries, it displays how the tracing data is oriented and gives you breakdowns of to explore different dimensions of that tracing data. So this allows us to browse through the behaviors of the system without actually having to write these pinpoint queries. So with that, tracing helps us understand where latency is causing issues or where the error is coming from. But we want the other half of this question of how do I fix this problem, or what code is causing this latency or errors. In this case, for this, we can leverage profiling and Pyroscope to answer these questions. So I want to quick talk about what a profile is. So in simple terms, if you have an application that's running, we can, over some fixed period of time, take point-in-time samples of the stack trace of that application and aggregate them together into a profile. So, and oftentimes profiles are visualized using flame graphs. And flame graphs have two important components. They have a width, which represents the total resource usage, and they have a height, which corresponds to the order of function calls in a stack trace. And so here we have a sample program which has two functions, do a lot and do little. And we've profiled this, and we have this corresponding flame graph, which we can look at and observe that the do a lot function is consuming 65% of the total CPU usage, and the do little function is only consuming 26%. So that's a single profile. Pyroscope offers this notion of continuous profiling. So a continuous profiling is taking those profiles and aggregating them over time. And Pyroscope, being a database for continuous profiling, has this ability where you can query and visualize these profiles at any point in time. So using a Prometheus-like labeling and querying system, we can select a time range and some labels and get a nice breakdown of resource usage over time, and also the canonical flame graph representation for that profile. And the business value here is twofold. We both have proactive value and reactive value provided by profiling. So for proactively, what does this mean? It means we want to cut costs early, we want to improve our ROI on features we're currently developing, and generally shorten the amount of time it takes to optimize code. Pyroscope allows us to do this by providing line-level breakdowns of the resource hotspots. And to kind of really underscore this idea, years ago, our applications were relatively simple. I wasn't alive years ago, but when they did exist, they probably ran on a single box. They're relatively, to today's standards, relatively easy to understand how they behaved and the costs associated with them. As time has gone on and user usage has gone up and features become more complex, our applications react accordingly. So now we have these complex, probably distributed applications. There's many abstractions around libraries and tooling for deployments. We have third-party dependencies like messaging queues that help facilitate this application to work in a distributed nature. We have observability infrastructure to help us understand how this application is operating. And all of this adds up, and it generally means systems today cost more to run. What profiling aims to do is, for minimal overhead, enable engineers to go to the parts of the system they do control and ruthlessly optimize those. As a result, we see a reduction in the overall cost of running a system compared to previously. And I really want to highlight this idea of the resource usage required or the overhead required to profile applications. So this image here, we can see the grayed out lines that are a little tricky to see. This is a real application that we run in Grafana, and the grayed out lines indicate the total resource usage of the application. And this yellow line that's on the x-axis and almost invisible is the overhead that profiling contributes to the total resource cost. And in this table, we can see that overall adds up to less than 0.5% of the total resource usage in this case. So profiling the overhead is quite low. So circling back to value of profiling, there's this reactive component to profiling value. And we want to take latency issues seriously. And we want to be able to respond to these latency issues quickly. So broadly across many industries, revenue is inversely proportional to latency. So as we see latency go up, revenue will go down. And this is true for e-commerce. If cart checkout times begin to rise, we see users begin to abandon carts and sales are lost. And if in video streaming and online gaming, if we begin to buffer in those environments, users are going to churn to other platforms. So continuous profiling helps in this case to keep businesses ahead of this curve and be able to respond effectively and efficiently to increases in latency, thusly saving revenue. Another reactive component benefit of profiling is it allows us to quickly respond to incidents. So here is a breakdown of an incident that happened internally within Grafana shortly after the Pyroscope team joined. And this is when Grafana took a very metrics-heavy approach to responding to incidents. There's a lot going on here, but the takeaway is that this blue line represents a service that's reporting 400 errors right here. And we see this recovery process broken down into three major sections. The first is the initial spike, where the system began to report errors, and engineers begin to triage the incident. And we see it dip down as they attempt a fix, and they roll it out. But as the fix begins to land, spikes go back up, so this attempted fix did not solve the root cause. And again, we see the same behavior as another fix is applied, and we see, again, a spike in 400s as the fix, again, does not solve the root cause. And by this third point, the Pyroscope team had been notified of this ongoing incident, and we were able to enable profiling on the affected service while the incident was ongoing. This gave the engineers the ability to immediately understand what parts of the code was causing the problem and was different, and they were able to apply a fix that directly affected the root cause of the issue. And so the previous approach was really guess and check. It was, we think this might be the problem, so let's try this fix. Had profiling been in place to begin with, the incident may have played out something like this. An engineer would have been paged. They could have used Pyroscope's diff tool to select a baseline profile where the system was behaving normally, and then select a profile where the system was behaving abnormally. And then Pyroscope will diff those two profiles and highlight what parts of these profiles are different and what parts are added and subtracted. And engineers can use this to quickly identify where the problem is at in the code. And this can help engineers be more effective at developing the initial fix that directly affects the root cause. And so the model here is a profile a day can help keep performance problems away. And to help with this, the Pyroscope team has the following roadmap. We really want to provide a richer integration with other Grafana Labs products. And so this means you can go from a signal to profiling, or from profiling to another signal, and really play off the individual strengths of each signal. And this will help the observability journey of everybody, whether it is trying to identify inefficiencies in the code or triage incidents. We also really want to focus on user-centric feature development. So this means we're looking to create features and prioritize features that directly impact use cases our users have. And thirdly, but not leastly, we want to develop this open telemetry first instrumentation. So the team has been working hard and is very active in the open telemetry committee to bring profiling as an approved signal in open telemetry. This allows you as application maintainers or owners to bring profiling in as a signal to your service without a bunch of vendor lock-in code and making it difficult to move on. So I want to cover some new features that the Pyroscope team has shipped. We've integrated with tracing, which this means you can, as you're browsing your traces in Tempo and you see a trace that looks unusual, you can request a profile that corresponds to that specific span. And this means if this allows the workflow of using Tempo to find where a problem is occurring, and then immediately having profiling in Pyroscope at your fingertips to understand why the system behaved how it did. Secondly, we've built out an AI feature. So flame graphs can be challenging for new users to understand. And oftentimes, even experienced users need to understand the characteristics and the shapes that of flame graphs that certain systems build. And this can take some time and it requires a little bit of intuition. So here we can feed the profiling information to an AI model, and it can give us some immediate root cause analysis performed, or it can perform some root cause analysis, and it can provide us with a few suggestions on, I think these things should be improved, or maybe try focusing on making these improvements to see an improvement in your performance. And we have this ability to interact. You have this ability to interact with the AI, so you can ask questions to further clarify solutions it's suggesting or root causes it might have identified. And here's my personal favorite, is Pyroscope integrated with GitHub. And so what this means is that if you have a flame graph, you can select a node of that flame graph and then get you some source code brought up on the side. And the source code has a line-by-line breakdown of how much resource usage each line contributes to the overall profile. This is super useful because it brings a ton of source code context directly to the profile. And you get this immediate feedback on how much each line is costing you. Additionally, in the proactive sense and the integrating with other products in Grafana, Pyroscope is currently developing a feature to integrate with K6. So now as you build out a new feature and you want to load test it and understand its performance characteristics, you can use K6 to run the load test, but then get a profile inline where you can analyze the line-by-line behavior of that feature. Then you can identify inefficiencies and fix them before users ever see the product, the end result. So in conclusion, we've seen how Grafana's observability suite between Mimir, Loki, Tempo, and Pyroscope each bring unique strengths to the table. Individually, each is very powerful and has a broad range of capabilities by themselves, but together they create this holistic observability experience that's critical for understanding and scaling today's applications in today's complex environments. And so with that, I want to say thank you.